Welcome back, everyone. Today we're stepping into one of the absolute strangest yet most beautiful corners of physics. We're going to explore a place where mirrors aren't made of glass, but of pure mathematics. It's this wild realm where every single particle you've ever heard of has a secret, hidden twin. And it's a place where scientists at the largest machine ever built spend their days chasing a material so unbelievably fragile, it literally vanishes the moment it touches our world. In this explainer, we're embarking on a cosmic detective story to uncover the physics of antimatter.
And by the end of this journey, you're going to understand exactly why this elusive ghost material doesn't just make for awesome science fiction, it actually holds the key to the ultimate existential question. I mean, just look around you. Look at the stars, the Earth, the chair you're sitting in right now. Why does anything exist at all? Well, the answer to that massive question is intricately tied to the very nature of antimatter.
Okay, let's dive into this. Here is how our investigation is going to unfold today. First, we'll look at the mirror universe. Then, we'll tackle the cosmic imbalance. After that, we're going inside the antimatter factory. We'll follow that up with reality versus science fiction, and finally wrap up with the remaining open mysteries. Section 1, the mirror universe. Let's transition right into our first suspect profile, because to really grasp what antimatter is, we have to look back at how it was first discovered. And incredibly, it wasn't found in a laboratory, but purely on a piece of paper. Our timeline begins back in 1928 with a young physicist named Paul Dirac. He was trying to write an equation to describe the electron, essentially trying to merge quantum mechanics with Einstein's special relativity. And his resulting equation was brilliantly successful, but it had this really weird quirk. It gave two answers. One for positive energy, which, made total sense, and one for negative energy, which sounded like absolute nonsense. But Dirac didn't just throw the math away. Actually, he boldly predicted the existence of an anti-electron. And get this, just 4 years later, in 1932, Carl Anderson was looking at cosmic rays in a cloud chamber and accidentally photographed exactly what Dirac had predicted, a particle identical to the electron, but with a positive charge. He called it the positron. That single moment set off a century of discovery, leading to massive milestones like the 1964 Kion symmetry experiments, all the way up to the astonishing quantum breakthroughs happening at CERN right now in 2026.
And this brilliantly illustrates what antimatter actually is. So completely forget that popular image of glowing purple sci-fi goo. Antimatter is quite literally a mathematical mirror image of ordinary matter. An antiparticle shares the exact same mass, the exact same spin, and the exact same lifetime as its regular counterpart. The only difference? Its electric charge and a property called baryon number are flipped. So the negative electron has the positive positron, the positive proton has the antiproton. It's like a cosmic reflection.
Which brings us to the deep mathematical framework connecting all of this together, CPT symmetry. That stands for charge conjugation, parity, and time reversal. It is an absolute bedrock pillar of modern theoretical physics. The theorem basically states that if you had a universe made entirely of antimatter, viewed in a mirror with time running backward, it must behave identically to our universe. Mind-bending, right? Searching for tiny, microscopic cracks in this perfect symmetry is the ultimate goal of today's most advanced physics experiments.
Section 2, the cosmic imbalance. And this brings us to what is arguably the greatest missing persons case in the entire history of cosmology, the disappearance of half the universe.
According to our very best models of the Big Bang, the early universe should have created perfectly matched pairs of matter and antimatter in completely equal amounts. And because matter and antimatter annihilate each other into pure energy the literal second they touch, well, the universe should have entirely destroyed itself. It should have left nothing behind but an empty bath of light. But cosmologists calculate a staggering number. For roughly every 1 billion antimatter particles created, there were 1 billion and 1 matter particles. Just a tiny 1 in a billion imbalance.
So, those billion pairs completely annihilated each other. But that single, solitary leftover matter particle, it survived. That tiny fractional surplus is what makes up every star, every planet, and honestly your own body. This grand puzzle, the theoretical, physical process responsible for generating this tiny cosmic imbalance, is known as baryogenesis. Solving this requires finding a violation of something called CP symmetry. Basically, it means nature must have a slight, built-in preference for creating matter over antimatter, and scientists are hunting for that exact preference right now.
Section 3, inside the antimatter factory. Let's move to and see how this builds into how human beings actually deliberately manufacture this fragile material today. Welcome to CERN's antimatter factory.
Making antimatter in a controlled setting is just a monumental engineering feat. First, they have to accelerate ordinary protons to near light speed. Second, they smash them into a dense metal target, which spontaneously creates this chaotic spray of antiprotons out of pure energy. Third, because that spray is way too chaotic to actually study, they have to carefully slow it down using specialized decelerator rings like Elena. And finally, they suspend these particles inside specialized magnetic penning traps in a near-perfect vacuum. They have to do it this way because the moment antimatter touches the ordinary matter of the container walls, or even just a stray air molecule, it instantly annihilates.
Now, what's really interesting about these recent findings is the sheer scale of the cutting-edge laboratory triumphs we've seen from these CERN collaborations. The LHCb team observed CP violation, that crucial imbalance we talked about, in heavy baryon particles for the very first time. Meanwhile, the base collaboration achieved the impossible. They actually held a single antiproton in a controlled quantum spin state for nearly a minute. They created the world's very first antimatter qubit, basically a quantum memory.
But perhaps the most famously asked question in this entire field is, does antimatter fall up? Well, the AlphaG experiment finally gave us a definitive answer. They carefully dropped neutral anti-hydrogen atoms in a vertical magnetic trap. The result? 80% of the atoms annihilated below the center of the trap and 20% annihilated above it. This definitively proves that antimatter responds to gravity exactly like ordinary matter does. It falls down. So that romantic sci-fi notion of anti-gravity balloons, yeah, that case is officially closed.
And the breakthroughs keep coming outside of CERN too. In 2026, the Tokyo University of Science published this truly beautiful finding regarding a highly unstable matter-antimatter hybrid atom called positronium. They successfully beamed this exotic hybrid through a grating and observed a classic interference pattern. This is huge because it confirms that even exotic, extremely short-lived antimatter hybrids perfectly obey the fundamental wave rules of quantum mechanics.
Section 4. Reality versus science fiction. With all this talk of exotic physics, it's time we shift gears and tackle some of the rumors. Let's separate the medical realities from the starships and doomsday weapons you see in pop culture.
You might not even realize it, but antimatter is actively saving lives in hospitals every single day. Positron emission tomography, or PET scans, elegantly harness antimatter. A patient is injected with a safe, radioactive glucose tracer. As this tracer decays, it naturally emits positrons. These positrons travel just a tiny fraction of a millimeter before hitting ordinary electrons in the patient's tissue. Then, they annihilate, shooting off 2 gamma rays in perfectly opposite directions. The scanner detects those gamma rays to draw a highly precise 3D map of metabolic activity, easily spotting things like tumors. It's absolutely incredible.
But what about using it to power a spaceship? Well, despite CERN spending roughly $100 million annually just to keep their facilities running, their entire antimatter output across a whole year is a microscopic 80 nanograms. I mean, that is completely invisible to the naked eye. We're talking about a tiny fraction of the weight of a single grain of salt.
And because the production process is fundamentally inefficient, literally losing 99.99% of the input energy, scaling it up is an absolute economic nightmare. To put this into perspective, to produce just a single gram of antimatter, estimates suggest it would cost around $62.5 trillion. That is literally more than the combined annual economic output of every single country on Earth. So the sci-fi dream of antimatter rockets and weapons, firmly and decisively crushed by the sheer physics and economics of production.
But honestly, the mundane reality is actually so much cooler than a sci-fi weapon, because it anchors the science right back to you. Antimatter isn't just made in multi-billion-dollar colliders, it's made by nature. In fact, a radioactive isotope called potassium-40, which is naturally found in bananas and in your very own body, undergoes decay that releases positrons. Think about that. Right now, as you watch this explainer, your own tissue is producing a tiny handful of antimatter particles every single day. You are, quite literally, a tiny antimatter factory.
Section 5. The remaining open mysteries. As we move into our final segment here, let's look at the lingering open cases in our cosmic detective story. Where's this whole field heading next?
The intense, ongoing efforts in this field are entirely focused on extreme precision. The CP violation we found so far in the standard model, it's still far too small to explain why we exist, so the hunt for new physics definitely continues. Teams are aiming to refine their gravity measurements down to a 1% precision to see if antimatter falls at slightly different rates than normal matter. And amazingly, teams like BayStep are actually proving they can load antimatter into portable traps and physically drive them in trucks to quieter labs for better, more complex measurements.
When we step back,
This entire field gives us a deeply moving picture of our own origins. We exist entirely because of a 1 in a billion cosmic residue left over from the dawn of time. That tiny mathematical imbalance in the primordial universe is the singular reason stars formed, planets coalesced, and you are sitting here today, capable of wondering about the universe.
So, the crucial point is this. To study our own origins, physicists have to battle a fundamental truth. The moment antimatter touches our matter-dominated universe, it will instantly annihilate. The staggering engineering required to just briefly hold on to this fragile ghost material, suspended in a vacuum, represents humanity's ultimate dedication to uncovering the truth of our reality.
We've peered into the mirror universe, and we've actually learned how to hold the ghost. But the biggest answers are still out there, waiting to be found. If a 1 in a billion glitch created us, what other unseen forces are still hiding in the mirror? Thanks so much for joining me on this journey, everyone. Keep wondering, keep asking questions, and I'll see you in the next one.